In the last segment, what we did is we talked about an alternative method using Fourier's law for determining conduction problems. And what we're going to do, we're going to begin by solving an example problem. And this is for the alternative method. And what this will do, it will show what types of things we can calculate using this technique. And if you recall, it was for the case of steady, so we don't have time derivative, no generation, and one-dimensional conduction. So let me begin by writing out the problem statement and then we'll work through it. Okay, so there's our problem statement. What we have a conical section, which is very similar to what we looked at in the last segment. We're told the thermal conductivity. We're given information about the diameter, and recall we needed to know the area as a function of position. So knowing the diameter, we can get the area. We are told the temperatures at the two surfaces of this conical section, and then we're asked to derive two things. One is the temperature distribution as a function of position throughout this conical section, and the second one is the heat transfer rate. So let's begin by writing out what we know, what we're looking for, and then a schematic. Okay, so that's what we know and what we're looking for, our schematic. And I won't put it in 3 dimensions this time. Okay, so that is the schematic. The assumptions that we're going to make, well, they're going to be the assumptions that we used for the alternative method. So those are steady state, two was that we're dealing with one-dimensional conduction. So that means that the surfaces are well insulated, as we've shown here. 3 is that there is no internal heat generation. And the last one, which enabled us to pull the thermal conductivity out of the integral sign when we derived the alternative method, was K is equal to a constant. So K is not a function of temperature nor position within the object. So for the analysis, what we're going to do, let's begin with Fourier's law. And we're going to follow in the same steps that we did before. What we need to do, we need to figure out the area as a function of position being x. So it is a conical section, so it has round cross-section. So the cross-sectional area at any point is pi d squared divided by 4, subbing in the value for the diameter. So what we can do, we can take this area that we have here and we'll sub it into Fourier's law and then rewrite and rearrange. So we get that equation, and what we're going to do, looking back at our schematic, we're going to integrate between this position and any particular x location. So we're going to come up with an expression for T as a function of X, and consequently we'll be evaluating the temperature at an arbitrary X. So that's what we're going to do now. So we get this equation here. Let's go ahead and integrate that. And recall the first thing that we're after, we want to be able to find T of X. So we have T of X in this equation here. Let's isolate for it. So we get that, and that gives us an equation for T of X, which was one of the things we were after. However, if you notice in this equation we have the Q of X, and we still don't know what that is. So we need to solve for Q of X, and how are we going to get that? Well, we're going to use the boundary conditions, and so we've already used T at X1. We do know T at X2, and that is T2, and so let's go ahead and do that in order to find what Q is. So we have this equation here. What we want to do, we want to be able to isolate for the heat flux and going through this conical object. So let's solve for Q of X. So we have that. Let's plug in all of the values. When we plug them in, we get minus 2.12 watts. So we have a minus. Why do we have a minus? Well, if we go back, let's take a look at our schematic, which was right here. We said that X positive was going in this direction. And notice we're going from a low temperature, 400, up to a higher temperature, 600. Consequently, heat's going to flow from the hotter temperature to the lower, so really the heat flux is in that direction, opposite the direction that we've shown it. And so consequently what that is telling us is that the heat flux is going from X2 to X1, and so it's consistent, it makes sense, and that's why it's a negative. So that is the alternative method for one-dimensional conduction in a conical section. What we're going to do in the next segment, we're going to look at applying same technique to cylindrical coordinates, and then after that we'll have another segment looking at applying it to spherical, and then we're going to start to consolidate things and make this into a technique that we can use for general 1D conduction analysis. So that's where we're going.